Hello, my name is Phan, and for my research project, I want to talk about the hemodynamics in the circle of Willis uh, and the finding in this research paper. So, what is the circle of Willis and its function? Well, when blood flows to our brain, the blood supply to the brain is divided into the anterior and the posterior circulation. The anterior circulation derives the blood from the bilateral internal carotid arteries, these two right here, and supply the blood to the majority of the cerebral hemisphere. The posterior circulation derives blood from the bilateral vertebral arteries, these two right here. And the circle of Willis is the circle in the middle and is a ring of blood vessels. These structures right here. It is a structure that provides a collateral connection between the anterior and the posterior circulation of the brain. Why is it important? Well, research has shown that only 41% of human population actually have a completed circle of Willis, and that some of it variation have been associated with a higher risk of cerebral aneurysm. This figure on the right here shows a sample of different type of circle of Willis through an MRI scan. In figure A shows a complete circle of Willis. B shows a complete anterior half and an incomplete posterior half of the circle of Willis. And in C shows a incomplete anterior half and a complete posterior half of the circle of Willis. And D shows the incomplete posterior and anterior half. And the research paper that I'm about to discuss uses various methods of simulation to analyze the wall shear stress on the vessels of the circle of Willis to try and find any correlation of the structure to the rate of stroke. In one study, they used a form of computational fluid dynamics to simulate the wall shear stress of different variation of the circle of Willis. And blood flow was modeled with a Navier-Stokes equation as an incompressible Newtonian fluid within a rigid vessel walls. A model of the circle of Willis geometry was approximated as a network of tubes around a cubic curves. A pulsatile inlet flow rate and a constant outlet pressure were used as boundary condition. It was found that differences in vessel radii and asymmetric branch angle greatly influences the wall shear stress magnitude and spatial distribution. An increased prevalence of aneurysm at the bifurcation with a large branch angle was also observed to their research. The simulations show a high wall shear stress at location where aneurysms are frequently found in anatomic variations known to be associated with the increased risk for aneurysm development in extra patients. And in this figure over in right here shows their simulation run by changing the radii of the vessels and also the angle of the bifurcations and monitoring the pressure developing within the vessel wall itself. Another study models the wall shear stress by approximating the resistance to flow, the vascular conductance, and branching. They specifically study the myriad variation that naturally exists within the circle of Willis, anatomical variations such as asymmetry, hypoplasia, atypical origins for vessels, and absence vessels. And what they found was that a lot of the variation exists in the posterior communication artery, including hypoplasia and asymmetry. So the posterior communication artery is these two right here, and in these pie charts, you can see that a lot of the variations are in there, including asymmetry and hypoplasia. And this graph right here shows their resistant flow, as in like blood resistant to blood flow, and that hypoplasia vessels have a greater resistant flow than asymmetrical vessels, but they both causes suboptimal branching for the vessel itself, which can lead to high wall shear stress. The last study uses microfluid analysis system to model to determine the flow dynamic data and create a numerical simulation for the analysis of wall shear stress and further analyze the different variations of the circle of Willis. The figure on the right here shows one of the many configuration of the circle of Willis that was tested, including the completed circle of Willis, various point of occlusion, and different combinations of absent arteries. So this shows the complete circle of Willis. So the duplicate anterior communication arteries and the absence of posterior communication arteries and the absence of the P1 artery, which is this right here. And this is the various occlusion point. But the real point of interest are these two rows right here, where it shows high degrees of pressure or high degree of wall shear stress in these combinations, and the hemodynamic analysis indicate that higher degrees of shear stress occur in the anterior communication arteries, particularly in the hypoplastic region of the posterior communicating arteries in the P1 segment. And so you can visibly see the simulation and this effect, and the effects different incomplete circle of Willis has on the wall shear stress of the vessel wall. So these results together indicate that the morphological variation of the circle of Willis may really affect the aneurysm formation, resulting from an increase in wall shear stress. But more research are needed to accurately predict the risk of cerebral aneurysm and predict cerebral aneurysm before it happens in patients. And this is my citation, and thank you for listening to my presentation.